Like because it includes.
So today, well, let me summarize the week for you. So we started on Monday. We had an introduction to the whole course, and then we learned basics of IJulia. And then we've been applying IJulia to a number of topics. The second class was on quantum spin chains. The third class yesterday was on classical partition functions. We saw that these two subjects were connected. Today we'll deal with something else. We'll deal with the free fermion formalism. What we will see is that whereas with spin change we had a restriction on number of spins that was, we were comfortable addressing with a computer, which was around 10. Here what we will do is we will deal with similar systems, but with sizes which are much larger, say 1,000. And we'll see that actually this formalism is connected also to the quantum spin chain, and we'll use it to solve the Ising model again, but this time on 1,000 spins. The same way that the quantum spin chain lecture was related to the tutorial, first tutorial, this free fermion formalism will be related to the tutorial that we'll have this afternoon. And so it goes together. And also, maybe the classical partition functions, I'm not sure we'll see much of it from now on, but the same way, yeah, but actually the homework that you have to do over the weekend will be related to the first and second tutorial. So please make sure that you finish the tutorials, okay? Because you'll have to use that content to do the homework, and also it will be important. We'll build on it next week. Very good. So Majorana operators. Today I'm going to talk about the free fermion formalism. Specifically, I'll talk about Majorana operators. And so let's start by considering first one pair of Majorana operators. This is going to be two operators, psi1 and psi2. They happen to be defined by the following properties. They're going to be Hermitian. And also, they anti-commute. So we'll have psi I, psi j, plus psi j, psi I equal to delta ij identity. So they are anti-commute. Okay, and what does this mean in practice? We only have two of these guys, so we can spell it out. So if we choose I equal to j, what we get is that psi I square is equal to identity divided by 2. Okay? And if I is different from j, what we get is that psi1, psi2 is equal to minus psi2, psi1. Very good. And you may wonder what this actually is. If we try to represent them as matrices, what we can find is one possible representation is this. Sigma x, in terms of polymatrices, would be the first one is proportional to sigma x, the other one is proportional to sigma y. Okay. So just to be sure, this would be 0, 1, 1, 0. And this would be this matrix. Okay? And also, if you want to think in terms of, maybe you are more familiar with fermionic annihilation operators, so this would be in terms of polymatrices. But if we want to talk in terms of annihilation, annihilation or fermionic annihilation operator, then what we have is that what is this? So A can be written as psi1 plus I psi2 divided by square root of 2, and therefore A dagger would be psi1 minus I psi2. Remember that these guys are self-adjoint or Hermitian. Okay, so this is just in case you want to relate these objects to more familiar ones. Okay, and then what we'll be dealing with today is Hamiltonians that are quadratic in these operators. For the case of just a pair, a single pair, the only Hamiltonian we want, the only quadratic Hamiltonian that we can write is of this form. It's proportional to, it's of this form actually, up to identities. Okay? And if you wonder what this is, well, you can write it using this connection to Pauli matrices. This would be epsilon over 2 sigma z with a minus sign, so this would be this matrix. And in terms of fermionic annihilation and cadation operators, it will look like this. Okay? Okay, so that would be for one single pair. We just had a pair of these operators, but we're going to be dealing with n pairs of such operators. So with n pairs, we're going to have psi n1, psi n2 for n from 1 to capital N. And we're going to be using this index I, capital I. Capital I is going to denote n and what is that? An alpha, where n runs from 1 to capital N, and alpha is 1 or 2. Okay? The compact notation. So we'll have that, as before, these operators are Hermitian or self-adjoint, and also that they anti-commute. So psi I, psi j plus psi j, psi I is delta ij identity. Okay? All right. And now the translation into Pauli matrices is definitely not that simple. There is a translation, but it's not so simple. We'll work with that during the tutorial. Okay, it's called a Jordan-Wigner transformation. And I'm not going to write it now. And then what we are going to be interested in is in Hamiltonians that are, again, quadratic in these Majorana operators. So our Hamiltonian will look like this. It's going to be some prescription I over 2. That is an interesting prescription to take. These indices have each 2n values. And then psi I, some matrix ij, psi j. Okay, these are coefficients, and this is quadratic. This expression is quadratic or bilinear in the Majorana operators. Okay, this is going to be the type of Hamiltonians we will be interested in. And the observation here is that, as we will see in the tutorial, this will be equivalent to a Hamiltonian acting on n qubits. Okay, so this is actually a matrix that is 2 to the n times 2 to the n. Okay, we will see that at some point. But if we look at this matrix here, this is only 2n times 2n. Okay, so this grows, the linear size of this matrix is linear in n, whereas this one is exponential in n. Okay, and the point of dealing with this formalism is that we'll never need to build these objects. we'll do all our manipulations. We'll manage to diagonalize this Hamiltonian by just manipulating this much smaller matrix. And this is what will allow us to go to n equal to 1,000, for instance. Because with your laptop, you can diagonalize a 2,000 times 2,000 matrix. That's not the problem. Okay? Very good. And I'm just going to introduce some notation. I over 2. I'm going to call a vector psi transpose C psi vector. Just it might be convenient from time to time to refer to all these psi I, psi 1, 1, psi 1, 2, psi 2, 1, psi 2, 2, etc. Psi n 1, psi n 2. Okay. It might be useful to just call them vector psi. And what else? Yeah, and then this matrix, see, you can always, because of due to the fact that these are Hermitian and they anti-commute, you can always restrict your attention to a matrix which is real, made of real entries. This is a 2n times 2n matrix made of real coefficients, and also symmetric, anti-symmetric actually, sorry. Okay, real and anti-symmetric. Very good. So today we will be concerned with Hamiltonians that can be written in this way. Okay? And what we want to do is to actually diagonalize these Hamiltonians. What does it mean at the end to diagonalize these Hamiltonians? At the very least, we would like to get the 2 to the n energies, okay, for that attached to the eigenvalues of this Hamiltonian. But actually, we'll proceed by identifying first n, or actually 2n eigenvalues here, okay, from which we can build the 2 to the n eigenvalues. So
why not 2 to the 2n? Like, why does 2 to the n energies in the Hilbert space of 2 to the n, 5 to the n?
So the Hilbert space is 2 to the n. And what I'm saying is that this matrix, right, you have a vector space of dimension 2 to the n, and a linear operator that it's 2 to the n times 2 to the n. Right, so if you diagonalize such a matrix, you only get 2 to the n eigenvalues, right? That's the diagonal part. If I draw a matrix and it has dimension chi here and dimension chi there are only chi diagonal elements. Does this make sense? Okay. All right, so what we want to do then is first diagonalize this and then relate the eigenvalues of this matrix, which is a small matrix, to the eigenvalues of the larger matrix. All right, so, but it turns out that diagonalizing a matrix with these properties is a fairly understood problem. So there is a theorem that says that if you have a matrix like that, then there exists some orthogonal 2n times 2n matrix. Okay, so that means this matrix R is actually real also, and R transpose R is equal to R transpose is equal to the identity. These are all 2 to the n times 2 to the n matrices. So there is a theorem that says that there exists R such that C can be written as R diagonal R transpose, okay? Where the diagonal, this is diagonal logwise, so it's going to be a matrix of the form epsilon E1 minus E1 0 E2 minus E2, and finally En minus En. where we're going to take the convention here that all these E's are non-negative, and E1 is the smallest of them in absolute value. Yeah. Okay, I'm going to take this convention. We can always reorganize them so that they are like that. Okay, so that's a theorem. What I can tell you is that it makes sense in that if you look at this matrix, it's still real, okay, and anti-symmetric. Okay, so for this type of matrices, by means of rotations, you cannot completely diagonalize them, but you can bring them into this form. Okay. Very good. So all we have to do then, or the way we want to proceed, is to use this. We want to take our Hamiltonian, which was written as I over 2 psi transpose C psi. And now we look at C. C can be written in this way for some choice of orthogonal matrix R. So we'll just do that. I over 2 psi transpose R d R transpose psi. Okay. And now we're going to define a new set of Majorana operators. Phi, which will be equal to, again, phi 1, 1, phi 1, 2, all the way to phi n, 1, phi n, 2. Okay? We have 2n of those organized as a vector, and we'll define it just by being R transpose psi. Okay, so linear combinations of the original Majorana operators. And then, by definition of what these phi are, we'll have that this is written in this simple form, which is simple in the sense that this is diagonal. And we'll take it in a second. We'll see what that actually means. But before that, I want to say that this linear transformation is such, since this is a rotation or orthogonal matrix, this implies that automatically these operators that we've defined here, they are not just linear combinations of this guy, but themselves fulfill exactly the same constraints. So they are a legitimate set of Majorana modes. They anti-commute. And this is something you can check. This follows from the anti-commutation properties of the phis, of the original modes. Okay? We have this, and we also have that they are Hermitian. Okay? So this is the equivalent of a canonical transformation. Very good. And now what we want to do is we want to look at the Hamiltonian that we're interested in diagonalizing, where we want to look at it in this form and see how we can make sense of this new expression. So we'll do this now. So what do we have? We've written, if you expand it, we've written this Hamiltonian as I over 2, and then sum over n from 1 to capital N of some eigenvalues, em, and then phi m1, phi m2 minus phi m2, phi m1. Okay, that's how the Hamiltonian looks like now. And I want to argue that this looks like, so first I say it and then I try to argue that this looks like n different copies of the single pair Hamiltonian that we analyzed before. And the important property is that these different copies don't talk to each other. So we have n problems, or the sum of n decoupled single pair problems, okay, which we know how to solve. So if you want, the way to see this is that this quadratic operator behaves as a bosonic operator now, in the sense that if you look at the commutator phi1, m1, m2 with somebody else, say n1 phi n2, okay, this would be for different values of n, right? So, well, you take this, and you see that actually if m is equal to n, okay, this is just the commutator of an operator with itself. So 0. But if m is different from n, okay, then these two guys are different from these two guys, and the anti-commutation relations imply that you can actually, you have two minus signs which account for a plus sign, so you compute the commutator and again it's 0. Okay? Very good. So what we have here is there are many different ways of seeing this. Maybe here are two possible ways. Let me first, so let me delete this. What we could do now is we could define fermionic operators, annihilation operators, by taking this phi m and phi m1 and phi m2 together in this way. Okay. And then, of course, you can always take linear combinations the way you want, but the point is that the anti-commutation relations of the phi's imply that this will be a proper annihilation, fermionic annihilation operator. And if you do that, then you can rewrite this simply as sum over from m equal to 1 to capital N of these eigenvalues, which I'm going to start calling single particle energies, and then a usual set of decoupled fermionic modes. Or if you want instead, you could, through this Jordan-Bignon transformation that that I have not explained, but you will work with in the tutorial, you could write this in terms of polymatrices again, and that would be sigma z's. Okay, and the Hamiltonian will look like, in this case, minus 1/2 of sum over m of 1 to n of these single particle energies times sigma z. Okay? So the idea is that indeed, after the change of variables that we took there, by using these new Majorana operators, our Hamiltonian turns out to be that of n qubits, where each qubit has its own sigma z, it's a magnetic field, and there is no interaction between qubits. Okay? So we know what the solution of this problem is. I mean, we know how to now build the whole spectrum of energies. Okay? When you have several spin 1/2 systems which don't interact with each other, what we have is this gives you the energies of each individual spin, right? Each spin could be up or down with an energy that would be, remember, so if we have a spin, we are in the spin up or a spin down, then the energy in this case is going to be minus em over 2 or em over 2. And we have to do this for each of the spins. So the energies, well, first we can ask what's the energy, the lowest energy that we can have in this Hamiltonian. And that will be, remember that all the EMs are positive, so the lowest energy will be when we have sum over all M's with a minus 1/2, right? This is the sum of all the single spin lowest energies. So this is going to define our ground state energy. Okay, that corresponds in the spin variable to having all the n spins 1 to n in state 0. And then you can build the full spectrum of energies by considering flipping just one of the spins. Maybe the first, maybe the second, but also flipping 2 spins, okay, and so on. So this is how you build. There are 2 to the n strings of ups or downs, okay? And the corresponding energies will be, so the energy, what we're going to do is we're going to define, what we're going to do is we're going to define some vector x, which will have n components, okay, where each of these x m could be 0 or 1. Okay, so we'll have 2 to the n such vectors, and with these vectors we'll specify what the individual qubits have spin up or down. And then the energy of attached to one such configuration is going to be the ground state energy, right, which comes from having always spin 0. But we're going to have to change the energy coming from each spin that has been flipped. So this is going to be, we're going to look at the energies of all the spins that have been flipped, right? If this is a 0, there is no contribution. If this is a 1, then we'll change. We're adding this energy. And that's it. Okay? So we have 2 to the n energies. Okay? These are the 2 to the n eigenvalues of this Hamiltonian. And we build them by using only this n energies, single particle energies. Okay? Is that clear? Okay. So maybe today I won't finish late. So why is this interesting? Well, I already, let me say this is interesting for 2 reasons. First one is these are systems of interest on their own. Okay? So systems of free fermions or approximate certain systems in nature. So we should be happy that we can solve such systems. But on the other hand, also, closer to what we've been doing here, the system is also of interest, or systems of this form, because they can be mapped to certain spin systems. Okay? And that's through a Jordan-Wigner transformation. So through a Jordan-Wigner transformation, we'll be able to map, actually the quantumizing model will be mapped. I'm going to put here equal, okay? But then I have to specify it's going to be mapped into this Majorana quadratic Hamiltonian, okay? And the only thing that will happen here is that there will be something happening with the boundary conditions. So up to boundary conditions. And what that exactly means, you'll find out in the tutorial when you try to relate the two. But remember that as I said, we've managed to deanalyze this guy with an effort that scales as 2n, that's the size of the matrices. Deanalyzing a matrix which is 2n times 2n comes with a cost that is only the third power, okay? You may or may not know this, but the cost only scales as n to the third power, and that implies, in practice, that we can comfortably deanalyze matrices that are compatible with n equal to 1,000, okay? So that means that we'll be dealing with n equal to 1,000 spins here, okay?
Why is this 2n to the cubic? I mean, why is
right.
it not a 2n to the square?
Right, so if we have a matrix that is chi times chi, this is the size of the matrix. If you try to multiply such matrices, two such matrices, okay. So what do you have to do? Okay, let me do it here. Oh, actually, I do have a space, right? So you have a matrix, which is chi times chi, dimensional. Let's multiply two such matrices, say m times n. This is, what this means is we have alpha, beta, beta, gamma. And we want this to be L, which is going to be alpha, gamma. Turns out that the type of operations that you have to do to deanalyze such matrices include matrix multiplications, and diagonalizing is done through something that amounts to matrix multiplication. So we need to understand the cost of multiplying two matrices. But now you see this, right? So what this means is we have to repeat. So let's suppose first that we want just the element, I don't know, 1, 1 here. So that's going to be sum over beta, which runs from 1 to chi, of m 1 beta and beta 1, right? So you'll have to do on the order of chi operations, right? You have to take on the order of chi such numbers and such numbers, multiply them together, and then make a sum. This is chi operations. So the cost scales as chi. But now it turns out that we have to do this, not just for these values, but for all values. And there are chi values here and chi values there. So we have to repeat this chi squared times. So the overall cost is chi to the 3. Okay? So that's why whenever we see a matrix of dimension n or 2n, the cost of diagonalizing it is going to be that linear size to the third power. Okay? Very good. Okay. So now we are almost ready to go and see how to do this with Julia, how to diagonalize this matrix. But before I do that, I want to discuss a little bit exactly what's going on. Why is it that we have these systems that suddenly we can diagonalize so easily? And so what is going on? Okay, so this is what's happening. If you compute for Majorana operators, if you compute a commutator, if you compute a commutator of a quadratic term with a linear one, this is really simple. You just need to use the anti-commutation relations, and you'll get that this is equal to some linear combination with coefficients I, j, k, l of psi l. Okay? So the important thing about this, it's simple calculation, but what I want you to focus on is that this is quadratic. This is linear. And this is again linear. Okay? And I want you to compare this to what would happen if you consider polymatrices. So with polymatrices, we have n alpha. If you consider again a quadratic term and a linear one, simple calculation says that this is a linear combination, again, sum with coefficients of a quadratic term. Okay, so now we have quadratic, linear, goes into quadratic. Okay, so if I had to summarize this or write the same in a very compact way, I would say this. Okay? What does this mean? Well, consider now the following. Suppose that we have our vector of fermionic or Majorana modes, in this case, Majorana modes. So, and suppose that we want to conjugate it by some unitary where the unitary is written as the exponential of some quadratic form. So with m is of the form I over 2, sum ij, psi I. Okay, let's make it easier. I just say psi vector, some e psi. So suppose that m is quadratic. Suppose that we want to conjugate our vector of Majorana operators by a unitary which is generated by a quadratic Hamiltonian, so to say. Then what you see is that for small epsilon, this can be approximated by psi minus I epsilon and the commutator of n with the vector psi, right? To first order. And now what we've seen before, what we've argued is that this is quadratic, since this is quadratic and linear, that this is going to be linear, okay? And therefore it can be expressed, this part here, this commutator can be expressed as some matrix, let's call it S or whatever, a linear combination of the psi's. That's what it means to be linear. So before you notice, you can rewrite this as identity minus I epsilon some matrix S acting on psi vector. Okay? And then if you want, we can, this was the first time in an exponential. You can further consider more terms. And this can be written as some matrix times the original guy. But remember, the point is that this matrix here is only 2n times 2n. Okay? Whereas this object here is 2 to the n times 2 to the n. Right? So now you could say, okay, fine. That's why this works. We have identified a subalgebra. We have in the algebra of all operators that could be acting on this Hilbert space is this big, the total algebra. But we've identified a subalgebra which is only 2n times 2n dimensional. It's a subalgebra. It's closed under okay, well, I'm not ready to say that yet. What I want you to think about is what this implies. What happens if we now consider instead our Hamiltonian, which is quadratic, and we conjugate it again. Okay. So this time the expansion will be, well, first we get k, then minus I epsilon, and then we get the commutator of m with k. But what we're saying is if this is quadratic, and this is quadratic, okay, now we just need to apply the rule, this here, which tells us, which implies that the commutator of a quadratic with a quadratic term, it is what? You take the first one out, gives you psi, psi, psi. You take the second out, so you get psi, 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 okay, with lots of indices. The important thing is that we just said that this is linear, so the result is quadratic, okay? So the commutator of quadratic with quadratic is quadratic, So we come here and we realize that we started with a quadratic Hamiltonian. When we conjugate it by a unitary, which is also generated by a quadratic form, then we get that again, the result is quadratic. Okay? So what we're seeing is that we have the quadratic terms here close a subalgebra. Okay? If we study Majorana operators that are expressed as quadratic or bilinear, that these guys close a subalgebra. Okay? So we can diagonalize such objects with similar objects without ever exploring the full algebra. So this form subalgebra of dimension 2n times 2n. It's a subalgebra of the full algebra of linear operators, full algebra, which would be 2 to the n times 2 to the n. Okay, so that's what's happening. If you try to do the same with polymetrices, you'll find that we have the rule here. So now if you try sigma, 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 quadratic and quadratic in polymetrices, you'll get that this is sigma to the third power. And every time you apply a new commutator, you'll get an extra power. So this will expand directly the full algebra, 2 to the n times 2 to the n instead. Okay, so that's why, that's what makes this magic, that we can restrict our attention to a much smaller subalgebra and of operators, quadratic operators, and we can efficiently compute with those. Very good. So now it's the time to connect our laptops, or at least mine. Can we have the screen down, please? Perfect. And also, can somebody adjust the lights? Oh, also, good. So let's open the notebook. That's Julia 4. And what I want to do here is very simple, and again, it's preparation for the tutorial this afternoon, where you'll deal with this type of problems. So let me start by writing a concrete Hamiltonian, which is going to be quadratic. And it looks like this. And you'll see it in the tutorial, so you don't need to copy this. You'll receive a piece of paper with this written down on it. Okay, something like that. So let me draw something that illustrates what this Hamiltonian is representing. I'm drawing pairs of Majorana modes. That would be first pair, second pair, third pair, and so on. Okay, and then this is 1 and 2, 1 and 2, 1 and 2. And the first Hamiltonian term is connecting n2 with n plus 1, 1. Okay, so n2, this guy with the next, with the 2 with the 1 of the next pair. So it's something like that. It's connecting these two guys. Okay, for all n's. Okay, that's the first term. Maybe I can say this term here corresponds to these links. And now the second term it's N1, N2. So it's connecting operators within the pair with some amplitude h. Okay? And this is obviously quadratic. And what we want to do is we want to write this in this more compact form, psi vector transpose C psi vector. And this will correspond to the following matrix. If you think for a minute, the matrix is going to look like this. It will be 0, 2h. So just by convention, we put divided by 2, and then that comes with a 2 here. We divide by 2, that comes with 2h instead of h. So that's this 2. Okay, so we have these blocks that correspond to single n's, n1, n2, n1, n2, and so on. And within this block, we have these terms connecting the first and second operator all the way to the n. So this block appears n times. Okay? And then what we have also is this 2, which will appear here, and a minus 2 there. Let me check. Yeah. So 2, minus 2, 2, minus 2. And then finally we close this, and there is a minus 2 up here and a 2 down there. Okay? I've just written the matrix C corresponding to this K. Okay? All right, so the first thing we want to do is to write down this matrix C. So we go to the first cell. And this is done in two, well, this function builds this matrix C. Okay, forget about the boundary conditions for the time being. What we do is we prepare this in two pieces. One corresponds to the central blocks, the other one to the other elements, and yeah, a couple of for loops, and that prepares this matrix. Okay, there is nothing magic about this part. So if you want to try it, for instance, for n equal to, I don't know, 2, that should be a 4 times 4 matrix. So shift. Now it's taking some time because it's starting pyplot, which we will not be using until later, but that's okay. Now we're done. So if you look at this matrix that we have here, it's precisely of this form. Let me try n equal to maybe 4 to make it more clear. Yeah. So, okay, you can see the blocks that I was describing and the 2 and minus 2 on between blocks, and then these two numbers out there. Very good. So let me put back n equal to 10 up here for later. Now the next thing we want to do is, well, there is some translation. This case translation invariant. Okay. So we will not only be computing energies, but we will also be computing momentum. So the expansion that I did for energies, right, we had n single particle energies, and we ended up with 2 to the n, multi-particle or many particle energies. We will do the same also for momenta. So first we need the single particle momenta. And the single particle momenta will come from building a translation operator. Okay? Turns out that this Hamiltonian commutes with a translation operator, which corresponds to taking each block and moving it. Okay? So we need to write also this matrix. Actually, oops, where is this? Yeah, that's enough. So this matrix, I'm going to call it translation F for fermionic. And it's just going to be whatever it has to be, such that it moves this block to the next one, And that is given by 0, 0, 0. And then, so the diagonal is made of zeros. And then 1, 1, 1, 1, and so on. Okay, so 0, 0. So we have these blocks of diagonal blocks. And down here, we have also one of these blocks. And this is the translation operator that we'll be using. Okay? And you can check that it commutes. So this function prepares this translation operator, and you can check that, which is of the form I was telling you. And then you can check, if you build them both, that these two commute. Right? So to check that C and TF minus TF and C commute, we can just build this, produce this guy, produce that guy, and check whether they are equal. That's what this expression here is equal is doing. And the answer is true. So that means these two guys commute. OK, and now, now we do what we do all the time. We simultaneously diagonalize matrix C and matrix TF. And I'm calling them 1 here because this was for periodic boundary conditions. But later I want to do also anti-periodic boundary conditions, and then I'm going to call it C2 and TF2. Okay? So there is nothing special about this code, but this code is the starting point for your tutorial this afternoon. So this code says prepare matrix C, prepare matrix. So for the Hamiltonian, prepare a translation operator. And here you can see we're going to diagonalize both. We don't need to use X. We can use, so we don't need to go sparse and only select a few eigenvalues. We can do the whole matrix. This matrix is 10 times 10 or 20 times 20. So there is no problem with that. We can get all the eigenvalues. Okay? And this is the trick that we discussed yesterday. We have some C1, or the matrix C and the matrix TF, and we want to simultaneously diagonalize them. We know we can do that. They commute. But we just want to make sure we break the degeneracies, and that's what we are doing here. And then what we did yesterday, to compute the single particle energies, we just look at them from the eigenvectors. This U contains, the columns of U contain the eigenvectors, right? The simultaneous eigenvectors of these two matrices, and now we just analyze the expectation values for each of the matrices. This gives us the energies, and this other gives us the momenta. Okay? Very good. And then we can plot it to see how it looks like. So that's what we are doing now. And we get a plot like this. So what I'm plotting here, it's the resulting K1. These are the momenta. So this is the momenta. You can see that it goes from roughly minus pi to pi. Okay? And in the vertical axis, what we have are the single particle energies that seem to go from 4 to minus 4. Okay? So this is for each energy, say E1, you have minus E1. There are 2n numbers here. Okay? So remember I told you that there was this orthogonal matrix. We had it somewhere here. We were saying that there is a matrix R, which belongs to O to n, okay, such that we can diagonalize this matrix into this fancy form, which was block diagonal with epsilon 1 minus epsilon 1, or E1 minus E1. Remember all this? All this was true, but in the end, at this point, we don't care about this form. We just want to extract the E's, right? We want the list of E1, E2, E3, and so on. And so instead of we will diagonalize the matrix using the most available simply available routine, which is by unitaries. So we don't restrict our attention to orthogonal matrices. And if we diagonalize this by unitaries, all that happens is that this becomes truly diagonal. Okay? So this becomes of this form. And we extract all these single particle energies and momenta, and we get some figure like this. Very good. But this contains E1, and so for any positive energy, you have negative energy. You see that everybody here has a doublet. There is degeneracy, so you don't see 2 points here, but at energy 0, there are two energies. And so all we care about, the single particle energies, are actually only half of those. Okay? We define them to be positive. So what we're going to do is we're going to, so this is a complete list of, we have a complete list of energies and momenta, and you see that for every energy, positive energy, you have a negative one with the opposite momenta. Okay? And now we're just going to reorder these energies so that we can throw away half of them, the negative ones, and keep the positive ones, which are the only ones we care about. And so this is done here. Sort permute. What this sort permute does is it gives you a vector, permutation vector, that organizes all the energies from smaller to larger. So, and then we use this permutation to organize both the energies and the momenta. So let me shift into this. And so after applying this, we obtain exactly the same energies and momenta that we had, but now they have been organized. If you look at the energy from the smallest to the largest, and we're just going to keep half of the list. We know that the upper half is just the same as these guys, but with a minus sign. Okay? So we're just going to keep half of the list, and this is done in the next cell. In the next cell, what we do is we have a vector with 2n components, and we are going to restrict our attention from now on only to the second half of them. So instead of going from 1 to 2n, we only care about those that go from n plus 1 to 2n. So what this is doing is taking a vector of length 2n and is replacing it with one that has length n only, okay? By keeping the second half of the components. And the same, we do the same for the momenta. And so after we can plot it again. The same that we plot before, and this time we see that indeed we only have the upper half of the picture we had before. Before there was this was completed into the negative energies. Okay, so we've selected our single particle energies, we've selected our single particle momenta, and they are here. And now we can repeat the same, but with anti-periodic boundary conditions. And anti-periodic boundary conditions only means that we're going to put a plus sign here and a minus sign here, okay? And that transition operator will also come modified with 2 minus signs. And we call this C2 and TF2. Very good. And then we do exactly the same that we've been discussing. And we plot the result. And the result includes in blue the previous calculation, and in red the new single particle energies. So blue comes from the periodic boundary condition, red comes from the anti-periodic boundary conditions. We just plot them here together, okay? And this gives you the complete single particle energies and momenta of the problem. And then in the tutorial you have to build the many, you have to start combining them and get the 2 to the n eigenvalues for both energies and momenta, and you want to relate this back to the Ising model. Okay. Okay. So yeah, I almost finished on time, and that's it. Any questions? All right. See you in the tutorial then.